We continue our discussion of solution of the Couette flow with applied pressure gradient that is acting with variation in x. Now we have determined a few terms, but remember we cannot convert from a partial derivative to a total derivative in equation 5 above because this time p is a function of x as well as z. So in the earlier part we had p as a function of only z, but this time since there is external pressure which is changing with respect to x, therefore p can be a function of x and z. Now we integrate the third component of the x momentum equation and we obtain u is equal to 1 over 2 mu delta p by delta x y square plus c1y plus c2, where c1 and c2 are constants of integration. These are the constants that are to be determined by applying the boundary conditions. Equation 5, for the z momentum component, we integrate once and we obtain p is equal to minus rho gz, and here there should be another constant of integration, but that constant of integration can possibly depend on x. So therefore, instead of writing c3 of x, we chose to write f of x, where f of x is to be determined by applying the given boundary conditions. Note that since p is now a function of both x and z, we add a function of, that is, f of x instead of c3, as I have just mentioned. So this is partial derivative, the integration with respect to z. It's important that whenever the derivatives are integrated, then the constants are chosen in such a way that the other variables that may occur, that may possibly be varying, have been taken care of. So, by carrying out the necessary integration, the final result for the pressure field is obtained to be P is equal to P naught into delta P by delta x times x minus rho gz. So we have earlier terms but another term introduced because of the pressure gradient that is being applied to generate the motion, and therefore we can see that it is playing a role in the motion. And then similarly, we need to apply the boundary conditions because we still have to compute what is C1 and C2. We have already computed the value for pressure, and when we try to find C1 and C2, we note that the values turned out to be, for C1 it's this one, and in earlier we only had this term coming in when there was no pressure gradient, but this time we have got another term appearing in the value of C, and it should be so because external pressure gradient is making a contribution to the fluid field, and therefore the total equation, and C2 of course is 0. So therefore the solution set will give us U is equal to V into Y over H. That's the part that we obtained earlier, plus all this other term, and this term is occurring because of the pressure gradient that is being applied to generate the motion. So the motion will take place in such a manner that is the way that external pressure is changing the fluid flow situation, and that is the solution that we have. So another term has been added. Now if we look at it, then we note that the velocity component u is combination of two terms. So we have capital V, into which is a constant, into y, which of course is changing, divided by another constant h, plus these terms. So the flow will be a combination of superposition of two types of flows or two terms. One given by this one, a linear flow, plus this flow, which by its looks, by its the way that it appears in the equation, will be deriving or will be generating a parabolic type of flow, which changes in a parabolic manner as far as y is concerned. We will discuss it by showing the geometry of the picture.